from the studios of Postscript Media and Canary Media.
I'm Lara and this is Catalyst.
If you're repeating these things in an assembly line process, you just get better and better and better at it, right? I mean, the simplest and crude analogy is if you've ever bought 3 IKEA bookcases, think how much faster, you are building the third one than you were the first one. It's a similar thing.
That sounds like a terrible Saturday, Jake.
It also is a terrible Saturday.
I've said it before, and I'll say it again. Today's nuclear energy is not the nuclear energy of the past. Technology innovations are making reactors smaller, safer, and more cost-effective. But nuclear is also one of those very polarizing and simultaneously unifying technologies in the climate tech space. It polarizes climate advocates, it forges surprising political alliances, and currently it's spawning a new generation of supporters on social media. So where should we stand on nuclear as a solution to climate change?
Let's face it, environmental news is often very depressing. That's why we focus on solutions on this podcast. But still, the climate crisis looms large. Rising temperatures, mounting pollution, environmental degradation, they're all warping the planet. And for a lot of species, including us, things don't always look so great. But the story doesn't end there. Every Friday, Living Planet, a show from Deutsche Welle, takes you behind the headlines to figure out what's happening and how we'll get through it. It'll also help you make better choices for a healthy planet and find space to reconnect with the beauty and wonder of the world around us. You can find Living Planet wherever you get your podcasts.
I'm Lara Pierpoint, filling in for Shayle Khan while he's on family leave. Congrats to Shayle. I'm the director of climate at Actuate, a nonprofit focused on systems innovation to accelerate greenhouse gas emissions reduction. Just a few episodes ago, Shayle and Scott Sue from RPE unpacked the exciting developments in nuclear fusion. One of the many reasons that fusion is awesome is that it offers clean power at exceptionally high energy density. But there's another technology that offers emissions-free electricity at huge scale and high density, and it's already commercially available. That's nuclear fission. Take a look at the last segment of your pinky finger. It's about the size of a uranium pellet and used today in a U.S. commercial nuclear reactor. Each one of those pellets holds the energy equivalent of a ton of coal or 149 gallons of oil. A stack of 18 of them will power your house for 6 years. So, why aren't we building lots of new nuclear power plants in the U.S.? One reason is cost. The only 2 nuclear reactors currently under construction in the U.S. are in Georgia. They were estimated to collectively cost $14.1 billion in 2009. As of fall 2021, they're still under construction, and the cost has ballooned to $32 billion. Meanwhile, safety, waste, and security concerns are derailing formerly stalwart nuclear industries in Japan and Germany. I've wondered for a long time, does it have to be this way? Can we deploy at scale nuclear reactors that are cheaper, safer, and that produce less waste? The 40 or so advanced nuclear reactor startups in the U.S. certainly think so. Today, I spoke to Jake DeWitt, the co-founder and CEO of Oklo. Oklo is a trailblazing microreactor company, and they've got deep technical chops, solid funding, and a clear vision for how they're breaking away from traditional nuclear models in order to deploy megawatts of nuclear power at a time. I think you'll like it. So here's my conversation with Jake. All right, Jake, it is great having you here today.
Likewise.
Let's talk a little bit about nuclear fission. Why do we talk about nuclear fission? Let's go ahead and put this in the context of climate tech. What are some of just the basic benefits and, challenges associated with nuclear power?
Yeah, I think one of the great benefits is the fact that it can produce a lot of energy from a relatively small amount of material, and it does so without emitting greenhouse gases, right? It's a very clean source of energy, and it works very favorably with respect to how you can actually have, a clean power source that's also quite scalable. On average, it makes about 9% of the world's energy. In the U.S., it makes just under 20%, and it does make the majority of the U.S.'s clean power, which is a pretty important piece of it. Obviously, it has some concerns and considerations that root back to sort of its origination, largely, from a military application, and sort of the early stages of the technology that then led to some, I would say, public concerns and fears about it, based on, the fact that it does involve radioactive material, something that's hard for people to understand because we can't directly sense it. It's just an interesting phenomena. Like if we could taste I guess anyway, if you could taste or see radiation, then I think people would be a lot more comfortable. But since you can, it feels a lot scarier. It feels pervasive. It feels very, very dangerous. And on top of that, it is something too that in general, it has a history that sort of pre the information age, as I like to think about it, there was a lot more uncertainty about it. People felt a lot more distanced from the technology. It's complex, but it's not terribly complex to understand. And one of the things I'm really excited about is the fact, sort of in the modern information age where material is so much more available, folks can actually learn and understand the details on the technology a little more readily, which I think helps sort of accelerate that. But anyway, sorry, I kind of got distracted there. Going back.
No, that's great. I mean, so let's dig in on actually exactly that point. Let's start breaking down some of the elements of nuclear to help folks kind of navigate what exists in this space. So we're going to get pretty deep today into advanced nuclear, which is to say some really cool things that are happening from a technical perspective to solve some of nuclear's challenges. But let's start by baselining where we are now. So you mentioned that 9% of global electricity is produced by nuclear power plants. These are generally big power plants. They're, kind of known as traditional nuclear. So let's characterize this. What's a traditional nuclear power plant? What are some of the basic features? And then let's get into kind of where we are with deploying traditional nuclear. What does the trajectory look like for traditional nuclear plants?
Yeah. At its simplest form, it's basically a way to make steam, to make electricity, right? And you do that by splitting atoms, capturing the heat from that. Today's reactors run using water as the coolant. It operates at pretty high pressures and therefore pretty high temperatures. And then basically that water flows through, cools these nuclear fuel pins that are these cylinders of basically metal containing these ceramic fuel pellets. And the fission process produces heat in those pellets that then ultimately is carried by that water over to a boiler, where you basically boil steam or boil water to make steam to drive a turbine and make electricity. They typically, on average, are about 1,000 megawatts in their electric output, derived from about 3,000 megawatts in thermal power. So pretty big systems. They run for typically a year and a half before they refuel. And on average, each reactor refuels about 1/3 of its core every, 1.5 years. So it's kind of neat in the sense that you have a lot of energy sort of contained in a relatively small amount. You don't have to refuel it constantly. You don't need trains going there, every day. You don't need big pipelines powering it. So you have some resilience baked into that. They operate at high pressures, so they have pretty big components, and that's kind of part of the aspects you see why they've gotten really big, because of economies of scale have driven that largely.
And I think one other point just to add to your list, which I think was great, I think that was a good characterization of what it's like. They also have really high capacity factors.
Yeah.
So nuclear, we use our nuclear plants really a lot of the time. And I know that at least in the United States, that refueling outage where you have to change out the nuclear fuel, we've managed to shorten that down to 6 and in some cases like 4 weeks. And so then pretty much the rest of the time the nuclear plant is operating, which is pretty cool.
Yeah, when you can hit 90+% capacity factors, it makes a big difference, and it's a nice firm fixed sort of asset, right? That can make power that's clean and run for a long time and be very available.
So theoretically, a great source of potential power for the world, particularly in a moment where we're really concerned about climate change. So what's happening right now? I know we're building reactors in some parts of the world. There are some countries that are actually pulling back from their nuclear power plants. Can you characterize a little bit of what's going on globally with respect to sort of the traditional nuclear trajectory?
Yeah, so right now there are about 440 reactors worldwide, mostly of the nature I described. There's some variations on that, but mostly of the nature I described. There's about 55 new plants being built around the world right now, including 2 in the United States down in Georgia. And there's a lot of interest going on, driving new ones, as well as a few countries that are driving to retire their plants. On the sort of retiring front, Germany, as an example, Austria has made it clear they aren't interested in their nuclear plants. They're retiring them. There's a few other countries in parts of Western Europe that have sort of been on the spectrum of looking at shutting down their existing plants, Switzerland and Belgium. Some possibly leaving the door open for new plants, though, over time. And then over, sort of around the world, over in Asia, obviously Japan's kind of continually evaluating how they're going to be approaching nuclear power going forward, kind of with a mix of retiring some plants, keeping some operating, and kind of keeping an eye on what these new technologies might be able to bring. So you kind of have a mix of some countries that are looking at this of saying, not really interested in keeping our plants running, looking at ultimately phasing those out. Some other countries, have started to look at this more of saying, hey, we either don't have nuclear and we want it, or we have some and we want a lot more of it. I think interestingly, this has been driven over the last maybe 10 to 20 years, largely in countries in East Asia. China's been kind of leading that. China recently announced they're going to be building at least 150 new nuclear power plants. And then similarly, you have countries sort of basically spanning the globe that are announcing interest in building either a few plants or building a lot of plants. Notably of interest, I think, is sort of the surge going on in an interest in Europe as a whole, ranging from West to Eastern Europe. Just in the last year, it's been it's a fascinating, honestly, dynamic about how they're looking at energy security and also decarbonization, driving them to realize, hey, these new nuclear plants really provide the answer that we want here. And there's a big push right now, ranging from countries like Poland with a recent announcement, to Romania, to even France, who just recently announced, one of the world leaders in nuclear power, that they're going to be building at least 14 new plants, which is pretty exciting to see. And then, of course, back in the Americas, in the US, there's this whole new surge of advanced reactor development and innovation that's happening that I think is a pretty exciting sort of opportunity space for the technology as a field as a whole, because it starts to migrate towards, newer, different technologies that open up totally different markets, totally different business models, totally different operating potential.
Yeah, no, I think that's a great sort of overview and characterization of what's happening globally. And I think to sum it up, what I would say is that, it really sounds like there are some countries out there that are really bullish, that are going to build a lot of new nuclear power plants, and some that are really bearish and are literally shutting nuclear plants down now as we speak. And looking to keep some of their, existing plants shuttered. So it's really clear that, nuclear has some potential benefits, but also some pretty serious drawbacks that in some cases are really, forcing these dramatic, pivots away from nuclear power. And generally, we talk about sort of 4 dimensions, right? We talk about the cost of nuclear, which is pretty high. It's expensive to build a plant, at least from an upfront perspective. We talk about safety, which is certainly driving a lot of the concerns in Japan, particularly after the Fukushima disaster. We talk about proliferation risks. So there are security implications associated with some of the activities around, nuclear. And so this really gets into this question of, can you make weapons from some of the material that you're using, for example? And then the waste problem. You've got long-lived radioactive waste that comes out of nuclear power plants at the end, which is another big concern that folks have. So, one of the things that I think is interesting about the advanced reactor community is they're not out there just to build new technology for the sake of new technology. There's some really cool things that they're doing, but really, I know you guys are all actively working to solve those 4 problems. So let's talk about that a little bit. What are some of the potential advantages just in general that advanced reactors can bring to the table across those challenges?
Yeah. It's a great list of the main points to work on solving. In other words, one of the things I like to think about and why I work in this space is sort of at the highest level, right? If you have something that's clean, cost competitive, and safe, that's a pretty good combo, and that's what you strive to do. And when you look at kind of the fundamental drivers in nuclear technology, I just like to start here before I dive into these, because it kind of frames the overall potential that is what's driving this interest in these activities. It's one of my favorite metrics is the actual material intensiveness of different power sources. I think that's one of the best sort of fundamental, I would say, metrics by which you can analyze the true cost potential of a system. In other words, what's the total amount of materials required to make each gigawatt hour of energy produced over the lifetime of different power sources? And when you look at that, nuclear by far requires the least of all energy sources available to us today. And it's a significant difference and advantage. And that's mostly afforded by the energy density of the fuel. One of the coolest things about nuclear power is, when you split an atom, you're releasing almost 50 million times more energy than when you're doing sort of a combustion reaction with a fossil fuel. That's a huge amount. That number is actually so big, it's hard to fathom. One of the ways I like to think about it is it's basically the average difference between the speed at which an average human can kind of jog and the speed of light, right? So it's a massive change. It's just huge. So that's why it has such a great advantage on that front. And so when you need the least materials, you should be also able to be really the most sustainable, the most scalable, and the cheapest. So that was one of the big drivers, I think, that's caused a lot of people in this flurry of sort of advancement and innovation in the space to look at, well, why aren't we realizing that? Because the data points haven't borne that out, right? The challenges with new builds, especially in Western countries, with these big light water cooled, in other words, just water cooled power plants that produce 1,000 megawatts, they're years behind schedule, billions of dollars over budget on projects that already cost billions of dollars. And a lot of that ties back to some of the fundamental aspects on the design and how that ties over, into sort of how you integrate the needed features and capabilities of the plant to achieve the safety goals, as well as, have a system that operates reliably. And at the end of the day, like, this is where you see these really exciting advantages coming, right? So from kind of a baseline level, today's plants, building new plants like that are very big construction projects, right? You're talking about a big high pressure system that needs big heavy components, and it turns into big infrastructure projects. And infrastructure projects, are not things that necessarily, I would say, the West excels at as of late. I think we're getting better in certain areas, but it's definitely not nearly as effective as we've seen smaller, power projects that sort of de-infrastructure it, which is a weird way of, it's kind of a made up word, but like make it simpler to build, right? So like gas turbines, what we've seen there in terms of how modular they've gotten, look at how renewables have been built out, and on kind of small piece by small piece, but at the aggregate can be quite large and are much more approachable in those senses. So I think what you see is there's some interesting drives, towards simplicity and scale. And then that ties in with some of these sort of inherent advantages. So that's my big preamble to basically look at this going through cost, safety, proliferation, risk, and waste. So I'm basically on the cost side, driving to simple, smaller designs at the end of the day allows for a lot more, I would say, centralized manufacturing and fabrication. So you get rid of some of the stick-built, in other words, big infrastructure, heavy construction aspects of a plant. You simplify it, and you combine those attributes of how you design the plant for a buildability or constructability perspective with also the safety features. One of the things that's also, so it kind of segues into that aspect. One of the neat things about this new wave of technology is they're really centered largely around putting the physics that drive safe performance sort of naturally on your side. In other words, these plants take advantage of characteristics that make them self-stabilizing, self-cooling, so they only rely on natural forces to drive those processes. Therefore, you don't need these big extra systems that are redundant upon redundant and independent. And, you have to have basically a bunch of these things on hand for these kind of systems you have to rely on to turn on, and parts to actuate, motors to turn on, pumps to work, all this stuff to remove sort of all the extra heat and keep it going. In other words, you put the physics of safety on your side to remove that through inherent and passive means.
Really enhance safety that also at the same time helps to reduce costs. So you're getting simplicity, and I know in some cases you're also helping to take the humans out of the loop, right? Which can be a safety enhancement.
Exactly. Yeah. People sometimes forget, but like the weakest link often is human error for most systems, not just nuclear, but for most systems, right? So what you can do by simplifying what needs to be done just makes plants safer and also cheaper. And on that, I think it's just kind of an interesting thread to pull on from sort of a abstracted viewpoint. But when we think about nuclear's sort of technology development arc, in many ways, sort of the first macroscopic iteration for the first, maybe 50 years of the technology was, I would say, somewhat focused on taking, the reactor fuel and maximizing the amount of power you get out of it without regard to all the downstream effects. And I think what this new wave is saying, no, let's look at it instead of saying, hey, actually, let's take sort of the boundaries at which you can have all of the safety aspects you need of a plant to keep it cool, to keep it stable, just defined by basically the natural flow of air, for example, over parts of a system. And then, effectively optimize against that. So, maximize power against that. That leads to smaller plants, but it also leads to much, much simpler designs. So just like you said, it ties safety actually to the cost benefits, which is a big advantage.
Yeah, and let's pause on that for a sec, because I think this is starting to get into some of the technology classifications around particularly advanced reactors. And so folks may have heard, for example, we've been talking about traditional big light water reactors at the beginning, which is what we've built over the past couple of decades. A lot of folks come to me and ask me questions about small modular reactors and say, hey, those sound cool. Why aren't we building more of those? And then there's a whole other class, which we call microreactors, and that's where Oklo fits in. So, you mentioned that these big traditional reactors we have, they're built that way because of the economies of scale. By the time you're putting together a reactor pressure vessel and all the safety systems you need to operate that plant, you want to get as much energy out of it as possible. So just say a little bit more about what defines a small modular reactor versus a microreactor. And, and then you've mentioned some of the ways in which safety systems are simplified, but how else are you going to get the kinds of economies of scale you might need to make these cost competitive?
Yeah. So one of the things that comes out of driving the simplification often leads to smaller plants that are easier to build and cheaper. And that's led to, these kind of differentiations. And typically people think about small modular reactors as being reactors that produce up to 300 megawatts of electric power. So about 1/3 the size or smaller of today's existing plants. And, it allows you to have simpler parts, smaller parts that are much easier to fabricate and ship together and sort of reduce the amount of on-site construction needed, and take advantage of all the things we can do very efficiently, manufacturing and fabricating things in a controlled environment. And then it also allows for just smaller total project sizes and therefore total capital costs and total capital needs, which can really help, right? Financing a $30 billion project is a lot harder than a $1 billion project, right? But then even further kind of size reduction goes into microreactors, which are, I would say on average, people typically think of it as 50 megawatts of electric power or less. Systems that are suited to be sort of basically operated and generate power in a more decentralized or even distributed fashion, closer to points of use, even often, to microgrid applications or behind the meter applications, and open up the door for some interesting opportunities that are quite different markets of service than just, I would say, the big centralized plants. Both SMRs and microreactors also allow for some interesting industrial integrations, including direct use of heat, which is a big way to help tackle decarbonization. At the end of the day, nuclear systems fundamentally produce heat that we then do things with. And so they actually produce heat much more cheaply than they even produce electricity. So there's a lot of opportunities that can come with those for decarbonizing industrial processes with both the heat and the power. And I think one of the interesting things too on the size range is that also ties in with different modes of financing that become accessible at these different cost points, right? When you're talking about a $30 billion project versus a $1 billion project versus a $100 million project, right? There's a lot of different levers you can pull for each one. But the smaller you get, the more, commoditized that those mechanisms become and a lot more suitable for a wide array of customers and also, basically business models.
Okay, so let's dive into some of the technology, differentiators here. And one of the things that you mentioned was that, around some of the uses of nuclear, that it's not just electricity, it's actually heat. And so there are, and for example, you can actually use the heat directly from a traditional nuclear reactor. And that was something that I spent some time exploring when I was at Exelon. But it's not very high heat. It's about 300 degrees C. It's about the most you're going to get out of a traditional nuclear reactor. And some of these advanced technologies can go a lot higher. But let's talk about like some of the general categories that people tend to apply to new kinds of advanced reactor technologies. Maybe starting with what we call liquid metal cooled reactors. What does that mean? What's a liquid metal cooled reactor? And what are some of the big advantages of those kinds of reactors over traditional reactors?
Yeah. As I think about it, these different technology types ultimately have different benefits, which is why they're being, pursued compared to today's reactors. And you mentioned temperature, and that's a big one. Temperature capabilities or operating at higher temperatures mean more markets for heat, higher efficiencies on electricity. So that's where one of the ways liquid metals come into play. So liquid metals use literally what it sounds like, liquid metals, kind of like that Transformer robot dude, but not sentient coolants. But just like we don't see liquid metals too often in like our daily lives. That's one of the most common, I think, data points we have is seeing like from whatever that was. Did I say Transformers? I meant Terminator 2. Sorry, Terminator. Anyway,
now I got you.
Yeah, I don't know why I said sorry. So it's like that, liquid metal thing. Anyway, the reason liquid metals are interesting, and they're often either sodium or a combination of sodium, potassium, or lead, or an alloy of lead and bismuth. Those are the primary coolants, but there are other ones too people are looking at. Those are the ones I would say have most experience behind them. The reason people are often interested in them is because they're very good at moving heat. We all know metals are very thermally conductive. We buy pans that have, sort of like cooking pans that have, metallic properties that are favorable to thermal conduction. Well, liquid metals are just really great, right? Much better than water at moving heat. And they can operate at high temperatures, which is valuable, but they can also operate at high temperatures without needing to be pressurized. So you can use smaller, simpler components and simpler systems to do that. So that's a big driver why people look at them. They allow for, systems to be smaller, simpler, and they also have some very favorable characteristics in terms of their operating aspects for economic reasons and for safety reasons because they're so good at moving heat.
Great. And what about the disadvantages? I mean, one that I know someone pointed out to me once is a really simple one, which is you can't see through liquid metal, which, isn't really that big of a problem, but it makes some of your sort of instrumentation and some of the ways in which you might, be able to otherwise perform maintenance on the reactor and things like that. It makes things a little bit trickier.
Yeah, I mean, it is. You can't see through it. Some of them are very heavy, so they're a little more difficult to pump. So some of those technologies are just pretty different than what we're used to doing. Some of them can be somewhat reactive or quite reactive with air or water. So you just have to design the system so you ensure that those are either mitigated or protected against or just avoided altogether. Thankfully, a lot of these technologies we have a lot of experience managing, but it does introduce some different operational challenges. I think one of the things that sometimes gets forgotten is we as humans kind of operate either in air or in water. Those are our contexts for most things we deal with. And that not just because, of how we feel it, but also how we see through it or how we see it or how we feel it, liquid metals are quite different. So yeah, you can't see through them. You have to use some interesting things like ultrasonic sensors and things like that, which granted we've gotten pretty good at, but it does change some aspects around the operational and handling approaches. So some folks look at, how do you design around that? How do you design for that? How do you accommodate that? How do you try to build practice to make that more, commoditized? But those are some areas where they have some disadvantages in terms of how you can approach ultimately the design of a system and the operation of a system.
Okay, so we've talked a little bit about liquid metal cooled reactors. Let's move elsewhere on the periodic table and talk about salt cooled reactors. How are they different and what sort of advantages or disadvantages do they have?
Yeah, liquid salt reactors have some pretty neat capabilities that kind of build on what liquid metals can do, but add in some other aspects similar to what gas cooled reactors can do, and also some entirely new aspects. So liquid salts are literally what they sound like, salts that are liquid. So think of, it's not exactly, well, in some cases it's your table salt just melted. So they operate at very high temperatures, typically well above 500 degrees centigrade. So sort of that 500 to 800 degrees Celsius range, similar to gas cooled reactors can do. But also they operate not at pressure, unlike gas cooled reactors, but similar to liquid metal reactors. So that can be simpler components. They also have the ability to store quite a bit of heat. So you can take advantage of that. The drawback being they maybe don't transfer that heat quite as efficiently as they store it. But that's easy to manage, right? You just design for that. And similarly, they open up a door that's quite different than the other designs where you're typically talking about a coolant separated from the fuel. One thing you can do with liquid salt is in some designs, they also dissolve that fuel up into the salt. And that has some advantages in sort of how you can design and build the system and sort of what you can do on the fuel efficiency side. So there's some interesting attributes that liquid salts provide us.
So let's talk about a completely different kind of technology. We've talked about liquid metal and salt. Let's talk about an option that doesn't involve liquid at all. Let's talk about gas-cooled reactors. So these are reactors where you're actually using the gas both to cool the reactor and to move the heat around. Tell us about those.
Yeah, so primarily looking at systems that operate at higher temperatures, and gases tend to live well in those higher temperatures. What I mean by higher temperatures, too, is even hotter than liquid metals get to. Just to go provide some reference, liquid metal reactors often are sort of in the 500 to 600 degrees Celsius output. Gas-cooled reactors are often 600 to maybe over 800 and beyond degrees Celsius in output. They often use helium as the coolant. It flows through, removes heat from the fuel, and then goes and at the end of the day can either directly spin a turbine itself, or it can go heat up another working fluid like boil water and have the steam go spin a turbine and make electricity. They are typically slightly pressurized, more so than some of these liquid coolants that operate at not at pressure, but less so than today's large reactors, and have some of the benefits that come with sort of using very benign inert materials. So you can kind of simplify some of your material selections, despite you just need to make sure they operate at higher temperatures. And it's got some significant interest based on some technology experience we have here too. Some of the reactors in the UK that are operating today are gas cooled reactors that use carbon dioxide, and so you see some experience successfully on how you can navigate using gases to remove heat and manage that accordingly, and then those experiences playing forward into some of these new designs.
Awesome. Okay, so we've kind of talked about a couple of categories based on the differences in the coolants and really the things that are used to transfer heat ultimately to the application that you want. But there's also a class of reactors called fast reactors, and some of these can be used with different kinds of coolants. But when folks hear fast reactors, what exactly does that mean? What's the advantage that those provide?
Yeah, so that's one of the aspects about how we think about reactors is also the neutrons that are sustaining the chain reaction, right? Because at the end of the day, the way a reactor works is you basically fission a nucleus of uranium on average, and typically you spit out 2 to 3 neutrons each time, and you need one of those to go on and cause another fission event, and that's how you sort of sustain that reaction. In today's reactors, in that process, those neutrons are born going really, really fast. Typically about like 3% or so the speed of light, or something like 10 or 15,000 kilometers per second. So really fast. So we often slow those down to make it easier to manage that, which is what we do in today's reactors. And we do that by bouncing them off of water. Literally, the hydrogen in water is quite good at slowing them down. Other reactors use other materials like graphite. There's a number of things that are decently good at slowing neutrons down. Fast reactors, on the other hand, and those are called slow neutron reactors or thermal reactors. Fast reactors, on the other hand, though, they let those neutrons run as they were born fast. And so that opens up some different aspects to how they can operate. At the end of the day, fast neutrons, so they don't have a moderator. The neutrons are going quite fast. That makes them most materials pretty transparent to them, because faster neutrons are harder to catch. Just like if you try to catch a fastball from a major league pitcher, it's a lot harder to do that than just a nice underhanded toss. Similar kind of physics actually at play. A lot harder for a lot of materials to sort of interfere with those neutrons and absorb them, which can, open up more common materials to be used. So it's easier to use things like some of these liquid metals or some of these stainless steel materials or other materials. It also means you need a little more fuel, but it also means you're much more efficient with the fuel, because now the byproducts of the process of fission itself don't poison the reaction, because again, the neutrons are harder to absorb. So they're less likely, these byproducts are less likely to absorb them. And that's one of the attributes that people get excited about, is you get much higher fuel efficiencies. It opens the door for better coolant usage, more available, cheaper, better material usage. And it opens the door on the fuel side, not just to be more fuel efficient, but also in some cases, it becomes pretty viable and attractive to even recycle that fuel. So not just the fuel from fast reactors themselves that can be recycled, but even the used fuel or the waste from other reactors too. And those are all sort of some of the attributes and dynamics about why people look at them and why people are pretty interested in them.
Yeah. So again, really, really interesting class of technologies where there are certainly some challenges around how you actually manage the reaction when you're dealing with a lot of fast neutrons, but a really cool advantage in that there's the potential to recycle fuel and actually take what we think of as nuclear waste from traditional reactors or other kinds of reactors and use those as fuel in these kinds of reactors. That's great. So that brings us then to microreactors. What are microreactors and what's Oklo?
Yeah, so microreactors are power plants typically on the very small side, still making megawatts of power, usually on the order of, sort of basically below 1 megawatt all the way up to possibly 50 megawatts of electric power, and often use some combination of these kind of different coolants and fuel forms we talked about, as well as neutron spectrum, to sort of help you miniaturize these systems favorably. One of the things that's kind of interesting about microreactors is, at the end of the day, they typically are systems that are, because of their size, they're relying on pretty simplified physics, all sort of very natural and passive phenomena to move heat, to remove heat, and to keep systems controlled and contained. And they also need a lot less overall material, right, to work with. So they just become much smaller footprints of plants. They can be manufactured off-site. They can be shipped to where they're used. And you have very little, actually, site footprint effects. You don't need a lot of, I would say, deep construction and integration to go on a specific site. That said, one of the aspects too that come from these kind of technologies is also just a very different business case, right? All of a sudden you can site these things right next to or even in factories, or data centers or communities or villages or off-grid and remote areas that allow you to basically provide power specifically to them. One of the ways I think that's kind of an interesting, somebody said that I kind of like, it kind of fits with how you can think about microreactors. If you think about putting solar on your rooftops at like a neighborhood level, one way to complement that is put, microreactors sort of off to the side of the community, sort of like, park or pool or center that can help sort of, underground, right? So like in the community center basement, basically is what they said. I butchered that. But basically, at the neighborhood level, if you think about that, that's kind of what microreactors can open up for some interesting aspects. And you can use them to, produce both heat and electricity. But I think some of the most interesting things about these systems is they allow you to get a lot closer to the actual energy user. And they also allow you to pretty flexibly integrate with what they actually want in terms of heat and power, and open the door for some significantly different financing.
Yeah. So some communities might choose community solar, and maybe in the future there will be an option to choose community nuclear that could also, by the way, provide your district heating if that was something you wanted to build.
Yeah.
Which is pretty cool.
Yeah.
That's great. Okay. Well, that's a really helpful overview, I think, of some of the technology characteristics. And we certainly didn't exhaust that space. There are a lot of other kinds of technologies and sort of interesting things that various companies are thinking about doing. But I want to, take some time to really talk about the question I'm most passionate about, which is really scale. Like in my mind, I'm all about saving the climate. And so that means we really don't have time to waste and getting, technologies like this and other kinds of clean tech to the point where they're really making a difference. So let's talk about the pathway for nuclear, because it's not a super straightforward, we're ready to deploy all of this stuff tomorrow. There are some hurdles that need to be overcome and some timelines that we have to think about. But some interesting ways that advanced reactor companies are trying to tackle all of that as well. So maybe we can start with cost. So at the end of the day, nuclear is only going to scale if it's cost competitive with other technologies. So what are some things that advanced reactor companies are thinking about to try to make them especially cost competitive? And I know we've talked a little bit about, safety systems and making them as simple as possible. But how ultimately are you going to get lots of these on the grid, not just a few safe ones?
Yeah, it's a great question. I think it takes a fundamental rethinking in many ways across the whole sort of nuclear enterprise about how this is actually delivered. It's a fundamental different paradigm where it's not thinking about onesie-twosies. It's rather thinking about how we build these things and deploy these things like we do automobiles, airplanes, and, even ships, right? And I use those analogies on purpose because they're quite different scales, and that reflects the diversity of scales on hand here. I think one of the cool things here, a lot of these systems leverage actually pretty, I would say, available supply chains that are commonly seen in other industries, particularly in like the chemical and processing industries. In other words, pretty common materials, pretty common form factors, nothing hyper exotic that's needed. Sort of the biggest supply chain constraint is on the fuel side. And that's largely just because, the demand for new reactors is going to be much larger, I think, than what the current demand is. So that's going to really strain sort of the existing infrastructure capacity for making fuel. But I'm pretty confident that that's a very solvable problem. There's not a fundamental resource limitation here that's significant. It's mostly just building out the capacity to do that. I think similarly too, when you think about that, it turns into leveraging different aspects about how we actually assemble these things, right? And how you sort of mix dynamically. In different companies and different technology classes are taking different approaches here that sort of look at how much do you fabricate in a central setting, what parts fall into that, how much do you integrate there before you ship it out together. One end being sort of maybe microreactors where everything is put together, all on site, all together and shipped out, to bigger SMRs, still small plants, but bigger, where maybe the reactor vessel that has all these internals and all these other sort of some quasi-complex aspects built into it, all fabricated together. So then you just ship it out, stick it into the ground, and then load the fuel in, and then connect it to the rest of the plant to make electricity. So there's kind of a spectrum between those, right, for how you can put these things together and ultimately realize some pretty significant cost savings. But I go back to sort of that one point of at the end of the day, nuclear is a very low material intensive for intensity footprint. So it should scale phenomenally well, but it does involve thinking differently about these things. And that's going to be setting up new factories, new facilities, new capabilities and infrastructure to realize this. Or in some cases, leveraging existing capacity that's underutilized at sort of fabrication, in the fabrication space. So in other words, underutilized factories or even shipyards or things like that can really help leverage how we can build these things quickly and at scale. But it also ties in, and I'll just make this segue here on the regulatory side, which is a big one, right, in terms of how we match that.
Well, actually, wait, before you go too much into the regulatory piece, because I think it was really great what you said there. There was one piece I wanted to add, which is just on the topic of nuclear should scale phenomenally well. And I think we have to also, all be honest with ourselves about the history of nuclear here. And the truth is that when you look at the United States and you look at France, two of the places that have built the most reactors in the world, you see reverse learning curves, actually, when it comes to the cost of nuclear power. It actually increased over time, got more difficult to build an economically efficient nuclear power plant. However, in South Korea, you see something different. They were actually able to follow a learning curve that involved actually reducing the cost of their plants. But I think it's an important thing for us all to keep in mind that it's not just about the cost estimate of that first plant. It really is about what do you see as kind of the ultimate, scaling equation for these plants and what are the costs that they're going to get to. And that's one of the reasons, for what it's worth, that I'm really kind of bullish on microreactors, like above some other things, because you really see this opportunity to, build these in a lot of different contexts and ultimately to have something that looks a lot more like a real learning curve where the costs come down, which I think is really important.
Yeah, I think that's a great point. Like there's an institutional sort of learning curve on cost that is almost always favorable in factory settings, right? If you're repeating these things in an assembly line process, you just get better and better and better at it, right? I mean, the simplest and crude analogy is if you've ever bought 3 IKEA bookcases, think how much faster, you are building the third one than you were the first one. It's a similar thing.
That sounds like a terrible Saturday, Jake.
It also is a terrible Saturday.
So we've been talking a little bit about some of the cost aspects and specifically about how some of the supply chain advantages, that really advanced reactors may confer could make a difference here. But let's talk for just a sec about financing, which is an aspect of cost and certainly relates to the discussion last week. So, one challenge with a traditional nuclear reactor is that financing one of those basically requires, betting the entire balance sheet of a utility if they're going to do it themselves, right? This is a huge thing. So already, if you've got smaller nuclear reactors, you've got some advantages potentially from a financing perspective. But say a bit more about advanced nuclear reactors. Are there certain things that advanced nuclear reactor companies are doing or innovating on to try to find ways to get, better financing terms going forward?
I think it turns into a diversification of both size and in actual product. In other words, it can be about heat and electricity, or just heat, right? Or just electricity. And those together open up the doors for some pretty, I would say, creative, but also well-exercised mechanisms by which you can finance these plants. And they come with, generally speaking, significantly lower total costs, especially at smaller sizes. And that affords some different business models that are being developed, where instead of, for example, just trying to sell the power plants to utilities, maybe instead you're actually just selling the power to the utility and or other off-takers, including straight to consumers, whether that be industrial users or even, actual individuals through power purchase agreements or similar vehicles. And that's been so well, I would say, exercised, right, that it's become fairly commoditized in the space for how we look at solar projects and wind projects in many cases. And that's great because if, financing a nuclear plant that's a $10+ billion build or bigger, it's a pretty complex financing transaction, right? And not a lot of people really want to jump to do that. But when you're talking about building on something that there's a lot of providers for and it's well understood in terms of an energy project, it just looks a little bit different because now you're selling power that is sort of a firm fixed output and can be dispatchable and has some capacity benefits available to it. That can be a pretty attractive thing for not just the financial community, but also obviously for customers. So together that makes a really attractive mechanism by which you can finance these things. And the size of these kinds of projects look more similar to different grid scale renewable projects, right? If you're talking about building like $100 million or less plant that produces, tens of megawatts of power, that becomes something that looks pretty similar to what's done out there. And then you can also bring in mechanisms like insurance into play, right? Like project finance insurance. And that can really help manage risk on these deployment cases, especially for early deployments. So you can afford to buy yourself down through that curve, sort of the learning curve and the cost curve on that, especially with these smaller plants where you can largely, assemble these things in factories and sort of forward finance against that to your inventory, if you will, that you can build out. So there's some really different ways in which we think about financing here. Different to nuclear, the old ways of doing things, but very familiar to the rest of the energy finance world. And I think that's a really powerful combination.
That's awesome. I cannot wait to see Oklo pioneer the nuclear energy as a service model. This is going to be amazing. Silicon Valley is not ready.
We're excited about that.
No, I love it. I think it's a really cool idea. So yeah, but now let's get back into this point about the regulatory side of things. And this is another piece where, venture capitalists, I think historically, although much less so now, excitingly enough, have been really scared of the nuclear space, in part because of how heavily regulated it is. And you guys within Oklo are really on the front lines here. I kind of think of you honestly as like there's this regulatory jungle, and you guys are like literally the vanguard out there, like cutting through this with some successes and some setbacks. So let's hear your perspective on this. Like, how is the regulatory environment? How well suited is it for advanced reactors? And what do you think is the future here? Can we have a regulatory system that really protects the public, but also enables us to do what we need to do to build carbon-free technologies?
This is a great question because of how significantly important it is when we talk about what the potential is here and also those pathways to scaling. It's a fundamental function on the regulatory side, right? And I'll just say, I think to answer your question, how capable is this to happen? I think at the end of the day, it should be very, very minimal because you're bringing forward technologies that have these natural safety characteristics that really scale well for what, enabling the regulators to do what their job is, right? Which is to protect and ensure, public safety. That said, they look different than what's been done to date. And that's where it becomes challenging. And in many ways, I would say there's been great strides made in sort of the Western regulatory world, but their record has been abysmal. So just to point at a high level, I think it's a data point that I think is interesting. There have been very few successes in the last 40 years where plants that have submitted their initial applications to not just the U.S. Nuclear Regulatory Commission, but any Western regulator and had those plants actually built and operated. Now, that's not all the regulators' fault, right? Part of that's economic conditions and market conditions and all those things. However, there's a definite aspect there that suggests that there's, I would say, some degree of even being out of practice in the regulatory space. So thankfully, I would say at a level of, at a policy level, there's been a significant bipartisan commitment and even to maybe mix terms here a little, but even somewhat of a significant grassroots and environmentally centered approach to sort of drive the regulator in the United States specifically to be more modern in terms of how they can be prepared to look at these new technologies. In other words, push them to modernize and transform, right, from how they've been doing things before. And what's been encouraging is there's been a lot of great progress made. If you think about what the NRC is, fundamentally, it's a pretty technocratic agency with a lot of engineers and staff, and they know how to look at these technologies and generally understand them. And what the key, though, is preparing them so that they can also look at these technologies and understand them through sort of the right lens and not necessarily through the lens of the past. In other words, these are not, as you say, your grandmother's reactors. These are not big light water power plants. So they fundamentally look different and have different attributes and meet and achieve safety in different ways. So what does that look like in practice? When I talk about natural safety characteristics, sometimes people say, or I say the terms even, and other people say, oh, they're passive or they're inherently safe. What those ultimately mean is they rely on natural phenomena to keep the plant safe, right? So in other words, if you lose the ability to, if all the sort of similar to what happened at Fukushima, and this actually can be referenced exactly to a real reactor that was built and operated and tested through this, if you lose the ability to actively drive cooling trains, so you lose power to the site, well, it doesn't matter because just the natural circulation of air just around the system actually removes all the heat you need to remove to keep everything cool. Well, and that's fundamentally just a function of, the natural properties of air, which don't really change, and gravity, right, which similarly doesn't really change. So those things are pretty favorable attributes to have on your hand or on your side. However, that's a little different to look at, right? So you have to think about how do possible pathways for heat transfer, right, degrade or change, and how do you characterize that and have confidence in that? Well, it's very readily doable, but those are some of the questions that are somewhat hard to approach in the regulatory space. Now, the NRC has made great strides, but again, you have to look at these things sort of towards their actual safety attributes. There's also process challenges, right, on the regulatory side. In other words, the system has been built for the plants that are operating today. And if you think about the Nuclear Regulatory Commission, it largely was stood up after sort of its predecessor agency, the Atomic Energy Commission, was the one that was sort of pioneering a lot of the new ways of, or not new ways, but pioneering the technology development and the regulation of it. And so it got stood up more in an operating culture regime than sort of a new design and build regime. So much of the NRC is focused on sort of regulating the existing operating plants that when you come in with new designs and new things, there's a lot of, I would say, like inertia and process that has to sort of be rewound or just discarded and built anew. So the NRC's done some good things in that space. They've implemented some good lessons learned, but there's still bumps on the road. And our approach fundamentally is if we take these advanced reactors and try to license them like today's reactors, we fail, right? Because they're going to be, it's a square peg, round hole problem. You can't, your apple orange problem, right? You can't make an apple into an orange or an orange into an apple. So don't try. Instead, focus on the fundamental drivers for public safety. And the regulations themselves are actually fairly generic. They're not entirely, but they're fairly generic. So you can meet them. There are pathways to do that, but you're going to have to try new things. And that's what we did. So, we became the first company to formally engage in pre-application with the NRC, which is where you familiarize them with your technology and socialize how you're doing it. And then also start iterating on regulatory approaches based on feedback from them. And that led us to piloting an entirely new application structure and process that then we got feedback on to turn into a real application that we submitted in March 2020. And then we got that accepted for review in June of 2020. And what was important about that was it looks radically different. So it's also not your grandmother's license application. Instead of being a 10,000 plus page document, it was, 600 pages. It was, which by the way, mind you, is actually still a higher page per megawatt count than other plants. So it doesn't scale perfectly like that, but still significantly more efficient. It presented the safety case in what I would call a more more logical and narrative case. In other words, it wasn't sort of checking this disparate set of boxes based on sort of the stovepiping of previous sort of regulatory experience based on the operating plant. It's instead sort of weaving the whole story together and presenting it there. And the NRC was able to accept that and review it. I mean, that people thought that was impossible even weeks before we submitted the application. So that was great. Very exciting to see that progress. But of course, then, early this year, so a couple months ago, I guess a month and a half ago, so June of 2022, the NRC punted it back to us. They denied it initially and said, hey, we need some more information on this to actually review it fully. So, come back, you fill it in and come back to us and resume. At the end of the day, being a first mover, everyone pays attention to that. It's like, oh man, what is all this? In practice, that's what it is. Hey, the NRC made a lot of good progress on this. There's still work to be done by them and by us. And some of this has to also, when you're doing something fundamentally new, you're going to, like you said, you're in the jungle, you're going to come up, you hack your way through it, and all of a sudden you're up against the cliff. You can't go up it, right? You got to now double back and figure out where you're going ahead. I wouldn't even say it's that extreme. It's more just like, okay, we came across a stream. Our initial pathway to cross it isn't really doable. So we're going to go a different way. But what I mean by a different way is like, we're just going to build a rope bridge. This is a really bad analogy, but point is, this is a doable process. And while that was a little bump in the road, we think these are fundamentally important, because if we tried to do this the typical way, maybe we'd be on a clear path to get a license, but it would be so inefficient that at the end of the day, the end product would be a very, very convoluted license that tries to mix attributes of different technologies together, and it just would not be efficient. So I think this is also where the culture of the industry has to adapt correspondingly with the NRC. There have to be more efforts to push and change things. And when you're doing that with a regulator, you're inherently going to face challenges. But the regulator's shown they can be adaptable, right? They've done new things in the past, and they can do new things here. And if anything, what we've shown in the past few months past really almost 2 years, they can do things radically different in ways people never thought possible, which is great. And again, these aren't trying to come up with totally different things like, oh, we're just not meeting the regulations. It's no, here's how we're meeting the regulations. It's just different approaches on how we actually map that and show we do that, and then commit to that in how the plant would actually be operated and maintained. So yeah, anyway, that was my soapbox.
I think that's really helpful to kind of understand the regulatory landscape. I think part of what some people may not fully realize is that really what we're called to do, what the regulator is called to do for advanced reactors, is a paradigm shift. And to give an example of what I mean by that, really originally when the NRC was regulating traditional nuclear reactors, they had a philosophy that they called defense in depth. And so that meant you have to put basically as much concrete as the walls of this nuclear reactor will bear in order to protect the public. And over time, folks started realizing this is actually not the most productive way to do the regulation. And so the philosophy shifted to one of performance, and where you're, regulating the performance of the reactor and saying you need to meet certain things. And now, of course, we're in this world where the advanced reactors don't really fit all of those, performance regulations perfectly, because there are just some fundamental differences about how they operate that they can't quite comply with the regulations as written. And so I think what you're pointing out here is that there are folks who could look at some headlines and say Oklo's, nuclear reactor application was denied at the beginning of this year, and say that sounds like a really big, scary, awful thing. But it's actually really part of this conversation and part of this healthy tension between advanced reactor companies and the Nuclear Regulatory Commission. And we obviously all need to move as fast as possible for the sake of the planet, but it's really important to get this right and to basically have a regime that is going to protect the public in all the ways that we absolutely have to, in addition to figuring out what's the right way to enable some of these reactors that bring advantages in that regard to kind of come to the table.
You're absolutely right. I mean, and even what you said before this, talking about scale, because scale is everything here, right? This is what comes here. And this is where I think this is why we're doing what we're doing. Because I can tell you with a microreactor, there's such a low overall hazard and threat that you could go in with a really, really kind of conservative approach and just, make your day a little easier in the regulatory space, because you're sort of going into, even going back in time, like you said, just these kind of ludicrous defense in depth kind of models and approaches. It's not a hard thing to do that and ensure safety and have a pathway there, but that doesn't scale. That does not scale, right? And I think fundamentally the current regulatory framework and processes as approached for light water reactors do not scale for these advanced technologies. So we fundamentally have to try new things. So I think that's where there's also a challenge, more so on the industry than just the NRC, I would contend, to bring those forward and to really push on those with the NRC, right? You have an industry that's pretty averse to doing new things often. And this is an area where there's a really good chance, a really important, I would say, opportunity and chance to try that. And the NRC has shown they can work in those areas. But you're going to fall down a little bit. When you learn to ride a bike, you don't ride it perfectly the first time. You're going to fall and scrap your knee. Right now, it's okay. That happens. And that's what has to happen. And that, to me, that's what has to happen. Progress is marked by that. And that's what I think we've seen happen in our experience. In a way, we've gotten through so much already that now we know how to approach sort of closing this out quite successfully, and similarly for the NRC. So I wouldn't say they operate as a completely capricious regulator at all, but definitely, obviously they have their opportunities to learn from this and how they can improve. And a lot of it focuses on things like project management and communications. It's not really about can they fundamentally do this or not? It's just, how do you do this efficiently? That's what it gets back to.
Well, and again, yeah, the way I tend to characterize it is kind of this notion of healthy tension, which is what I try to, communicate to my team working inside a utility and doing innovation is the fact that you run up against challenges. It's not because, people don't like you. It's because fundamentally we got to keep the lights on here. And in this case, fundamentally, we've got to protect the public. So there's some good reasons to kind of have this tension within the regulatory sphere. Okay, so we've talked about what I think are kind of two of the biggest issues that we tend to confront within, scaling questions, cost and regulatory. But I want to touch on just one or two more before we let you go. One is, let's talk for a sec about grid flexibility. So you mentioned, and it's true that nuclear reactors in some ways could be said to have an advantage because they're really kind of always on. They're always supplying electricity to the grid. But as we have more and more variable renewables on the grid, which is, of course, one of our other really great options for getting carbon-free power, how does this work? How does the system look? Can nuclear play well with renewables fundamentally?
Yeah, the answer is yes. I think they play, can they play? Yes, then they can play well. I think what's kind of cool is when you combine what renewables do quite well, which is a distributed, largely decentralized, clean, and quite affordable scale out of power production. That's great. And then you have to manage their intermittency, which obviously advances in storage help with, but so does flexible generation. And nuclear definitely can do that, especially these advanced reactor types where you can have, you can actually design them to be very responsive and flexible sort of by default. And when you talk about the fundamental cost attributes of these systems, it enables them to do that even better than sort of today's plants. And today's plants can still do that. But then you have some really cool innovations going on as well, not just on the reactor side, but on sort of how the reactor integrates with the actual power generation side, including integrating capabilities like, thermal energy storage, heat storage that can allow you to peak for hours at a time and match, really match sort of the mismatch where they may exist in demand and generation, especially in sort of those, sort of the 5 to 8 p.m. windows and things like that. So it's a really neat capability set. So if you think about it, right, Nuclear is really good at making heat, and then you can do a lot of things with it, including storing it. And that opens the door for a lot of flexibility options that can be quite accommodating. So I think it's actually like they integrate really naturally and really favorably.
Right. And what you're alluding to is potentially some ways in which nuclear can help not just with electricity, but potentially with industrial decarbonization, right? By supplying really carbon-free heat. Okay, and then the last one, of course, let's talk for a sec about waste management. Obviously, folks are a little bit nervous about the fact that nuclear waste is something that is really long-lived, and we have to figure out something to do with it. How are advanced reactors approaching that as a challenge? What are some of the ways in which they can maybe do better than conventional reactors in terms of alleviating our waste burden?
Yeah. So I think that's one of the cool things about these advanced reactors is they often implement ways to basically have higher fuel efficiencies and therefore associated less waste coming out of the plant. So that has a pretty significant upside. And that's afforded by them being, more efficient. You operate at higher temperatures, you make electricity more efficiently. And also on the fact that, at the end of the day, some of these fuel forms, and that's one of the cool things here, right, is there's a couple different fuel forms. Some use metal fuel, some use these coated ceramics, some use even fuel dissolved in liquid. All of those have different attributes that can really enhance sort of what the actual fuel use and fuel utilization efficiency looks like. And therefore, if you use your fuel more efficiently, it means you have less waste coming out of it, which is a great carryover. And then the other aspect that's really attractive, as we kind of mentioned before, is some of these reactors have the ability to recycle economically. So fast reactors in particular have some neat attributes where they can not just use this fuel efficiently, but they can use waste from other reactors and themselves quite efficiently and economically so, right? That's been one of the big hangups and holdups for recycling with today's reactors. It's just economically pretty hard. But some of these other technologies, it's a pretty significant paradigm shift thanks to the fundamental physics of the plants because they just use fuel in a much more efficient manner. And so you have a potential for radically simplified and reduced waste stream that can open the door for disposing the waste in coated glasses and metal forms that then you reduce the sort of storage times and disposal timeframes from perhaps hundreds of thousands or millions of years to maybe hundreds or thousands of years, right? It becomes a much more manageable approach. Plus, there's some really interesting innovations in the waste disposal side of things, like deep borehole disposal, that are really flexible for these kind of, or actually really accommodating for these kind of flexible waste forms. So you can dispose of this stuff in areas and it's, you can really secure and effectively ensure its long-term disposal until it decays away. One interesting weird paradigm of nuclear, especially when you talk about fundamentally recycling, is it changes the life cycle and lifetime of these wastes. So it's no longer about things running for it just decays away. In other words, you get the benefit of the fact that while it's radioactive, that also means it's decaying away. So at the end of the day, it actually does go away. Now, when you're talking about hundreds of thousands or millions of years, people don't care about that. But when you can reduce the time frames to like hundreds or even thousands of years, then people care, right? That becomes a lot more approachable.
Yeah, I think that makes sense. And I think, even though hundreds or thousands of years, that's still a pretty long time. I think part of what I commonly come back to is, if my choice is to manage nuclear waste for hundreds or thousands of years or manage a whole lot of greenhouse gases in the atmosphere, I'll pick managing nuclear waste every single day of the week. I mean, I think that's an easier engineering challenge, frankly, for us to approach.
Yeah, and I'll just quickly say that like the waste produced from generating enough power, basically in the United States, nuclear power has produced, a lot of energy for decades, right? Producing 20% of our energy for, 30 plus, 40 plus years. And then before that as well. And the amount of waste that's produced would fit on a football field being like, 30 or 40 feet high. So that energy density also means a much smaller volume of material to actually have to manage, right? So like you said, while you still have to manage it, it becomes a much smaller volume than the huge amounts of greenhouse gases that we obviously don't manage. So it becomes a very different paradigm about that.
Okay. So Jake, we've just had, a wide-ranging conversation about all of the, implications of nuclear power, where things are today, where advanced reactors are going to go. Sum it all up for us. How bullish should we be about nuclear energy as a solution to our climate challenges?
I think very bullish and very optimistic about the role it can play in helping us decarbonize. At the end of the day, these new technologies afford significant benefits across the board in terms of their, design, their capabilities, their economics, how they can integrate with the sort of evolving and dynamic grid that we're seeing emerge, as well as playing a big role in decarbonizing heat heat usage, which is going to play a massive, I think, role in industrial decarbonization. And on top of that, you're building on technology that has significant R&D already behind it. In other words, investments made over decades by sort of national entities has helped mature these technologies to be ready for the prime time they're entering into. So couple that with also, I would say a very attractive proposition that these smaller types of systems can afford in terms of cost and in financeability and in deployment timeframes. I think it can really make a big difference. It's going to take a significant, I would say, paradigm and culture shift around fission, but that's happening. That's what we're doing. We're working on our end of that, and I think others are too. And at the end of the day, progress will bear that out over time. So it's a pretty exciting time, I think, to be in the space, coming into the space. It's going to play a really important role in terms of coupling in with sort of our broad efforts to decarbonize, and it opens up different ways of thinking about how we can actually use the atom than what we've thought about before. And I think that's going to be a pretty significant, benefit for humankind.
Okay, so Jake, I just got to say one thing, which is for me personally, again, with my obsession with scale and my obsession for getting points on the board with respect to greenhouse gas emissions, we've got these emissions curve trajectories, and we need to drag them down immediately. So there's a set of things that we're going to have to do in the next 5 years to really meaningfully reduce our greenhouse gas emissions globally. Nuclear is probably a partial answer to that, given some of the bullishness in other countries for building new nuclear reactors, but advanced nuclear reactors in particular are probably a little bit further out. So just wanted to see, do you kind of agree with that? What do you think is the actual time frame in which we can expect to see, wide-scale deployment of some advanced nuclear reactors?
Yeah, I think you're right on the timeframes for what that looks like in that 5-year window. I think we start to see deployments happen in smaller scales in that time frame, but you're still talking about just a couple plants here and there. Ideally, that's setting the stage for a really great growth trajectory that really helps sort of into the future. But I think that's kind of where that transition starts to occur for nuclear. So in that time frame in the near future, it's, it is going to be something where it plays a role, but it's mostly finding its footing. I think there's some areas where perhaps if we as a sort of, I would say, society looked at that problem and said, how do we try to accelerate that? There might be some levers you can turn, but at the end of the day, it still takes time to forge and cut steel, and there's only so much you can get done in a 5-year window there. I would love to see us try to be aggressive and set some targets on that at a policy level for how we can leverage existing technologies more efficiently. In other words, there's some interesting things you can do building these plants, including bigger established plants in just slightly more innovative ways, as well as how we can help finance those things to get a couple of those going. But at the end of the day, it's really just, you can make some dents, but it's really going to play a bigger role in the time frame after that. I actually think the 5 years after that becomes really exciting for advanced reactors. Looking forward for the next couple decades for sure on the growth trajectory there. But yeah, it is a reality about what that window looks like over the next few years.
Right. So hopefully a really interesting couple of years to come, and a really exciting couple of years following that, if we really can do what we need to do to help deploy nuclear as a solution to climate change. Jake, thank you so much for joining. Really, really appreciate it. It's been a really fun conversation.
Thank you. Appreciate it. Thanks for having me.
Jake is the co-founder and CEO of Oklo. Catalyst is normally hosted by Shayle Khan. I'm filling in until he returns from family leave. The show is a co-production of Postscript Media and Canary Media. Find me on LinkedIn and Canary and Postscript on Twitter. Tag us if you want to provide feedback on this episode or want to suggest future topics. You can find links for this episode's topic and guest in the show notes, or go to canarymedia.com. Our producers are Daniel Waldorf and Stephen Lacey. Sean Marquand composed our theme song. I'm Lara Pierpoint, and this is Catalyst.